even when I talk about the Higgs, or whatever I talk, it all has to do with the fact that I can do, I can talk about protons, right? After all, what is LHC? It's a PP machine. And I can talk about protons just because I know how to talk about quarks. And I know how to talk about quarks because of deep inelastic. That's how it all started, remember? That's what we did last time. It's a short summary of what we learned, why you and I now know that quarks are the constituents of protons. Remember what we said, in order to know what is going on, if I want to look inside the proton, I need the short wavelength photon to hit it, right? It's going to be the electron which emits a photon, and that photon should go deep inside the object I want to find out. So we said the electron scatters, emitting a photon that, let's imagine a proton made out of 3 quarks, and then produces whatever it produces at the large momentum transfer. There is Q squared here. Sorry, there is momentum Q flowing. Okay, we call this momentum P, the initial momentum of the proton, and we call this final momentum what is coming out, P prime. Now Q squared, remember, was, so there is K here, K prime going up. Brief reminder, please ask me any question, okay? This you should comprehend, this is very important, okay? So if you didn't ask last time, ask now. I can slow it down, I can repeat it, we can do variations on this. Q squared is, so what is Q after all? That's K minus K prime, right? It's also P prime minus P, if I need. So it's K squared plus K prime squared plus minus 2K K prime. Now obviously if I want to do a deep inelastic scattering with Q squared, I'm going to ignore electron mass, of course. So this is 0. So it's negative. This we found out was minus 2 E prime 1 minus cosine theta. And this is often written, and really, I don't know why so much, one can just keep it in mind, but just to remind us that it's negative minus capital Q squared. So what I mean by deep inelastic is that Q squared is much bigger than mass of M squared. I call the proton mass capital M, somehow not to be confused. I also introduced another variable which was Q times P. That is also very large. Okay. To get a feel, right, sometimes I will compute this. I can talk about it in the center of mass frame. I can talk about it. So sometimes we can talk about center of mass frame. And there what I mean is that both electron and proton have huge energies, huge momenta. So proton looks like a pancake in a sense, right? There is a, it shortens the, this will be our proton, right? It will look like this, so not roundish as you would like to imagine, okay? It's very good. So in this frame, okay, we have fast electron and proton. I also often look at the fixed target frame where proton is at rest. Depends what I want to do. Just to emphasize, for example, in the fixed target frame, what is this? It's the mass of the proton and the difference of the energies. So this should be much bigger than M squared. So notice what we are saying, not only that the energies are large, but there is a large transfer of energy that's very important. I've noticed in the case when the electron just sort of passes through, right, we want to have a hard scattering. The transfer of energy very large, okay, this was, and we decided to keep X, which was Q squared over 2 nu, fixed. Okay, that was the idea of scaling. I can vary it, but I keep it fixed. What I mean that both of these guys are going to infinity in a sense, if you wish. Strictly speaking, I'm looking at the situation where they are huge compared to the mass of the proton. And what we wanted to compute was d sigma over d omega prime, dE prime. And we computed it in the fixed charged frame. We took proton at rest. And what we had was, you have your notes maybe? Alpha square, it was defined as alpha square q to the fourth E prime over E. This was really a definition of what follows. W mu nu is the analog of the polarization sort of tensor of the how to call it, of the lepton, of the electron. L mu nu we averaged over the initial spin of the electron, and there was a famous factor of 4. So we knew L mu from previous calculations, k mu prime plus k mu prime minus k prime g mu nu. See? This is a kind of calculation you can do easily now. You guys have been doing this a lot. Okay. And W mu nu, of course, I don't know how to compute it. And it's in general a complicated function. W mu nu, what we said, would have a number of coefficients. There will be a g mu nu. It's a function of p and q. So a g mu nu. I would integrate. I don't care what is coming out. It's just a function of p and q. I've taken this to variable. So there will be a g mu nu, b p mu p nu, we said, plus c p mu q nu, plus d q mu p nu, plus e epsilon mu nu alpha beta p alpha q beta. Then we have a situation in which parity is conserved. This is not going to appear. I don't even have to think about it. This is symmetric. So antisymmetric P does not contribute. I can drop this. Since this is symmetric, only symmetric piece of W mu contributes. So I can take C equal to D. And the current must be conserved, which simply means just to check, if I'm right, then Q mu, L mu nu should be 0. Please check. It has to. Current is conserved. But check it if you're not convinced. So I have only two functions W mu for W mu nu. Okay. It's not that bad. Right? Because there are three, but there is an extra condition. And we decided to write W as minus G mu nu. I think I took the sign. Anyway, I shouldn't have. This is called W1. Notice I'm writing just to make my life simpler, this in the explicit form of vanishing when I hit with commute. That's the whole thing in this notation. And the second piece was P mu. It's a combination of P mu, so this must be P over Q squared. Q mu, P mu. They must have the same dimensions. I choose them so that it's better. So this must be divided by momentum squared. So I call this W2 over m squared. Okay. energy square unit. And then what we needed to compute was L mu nu, W mu nu. It's straightforward. And we got 4 E prime to W1. I even did a calculation. I don't know if I've done all the factors right. I think I did. So there was 2 W1. 1 minus cosine theta appeared here, which I wrote as sine squared theta over 2. And there was 1 plus cosine theta. This was the final result. And then the cross section can be written as I use that k square is 2e prime, I use it here, so I'll get a factor of, so why don't I write here? This is minus 4e prime sine squared theta over 2. So there'll be 16, there was 4 there, I'll get to 1 over 4. E prime there, E prime will cancel, so I'm going to have alpha square over 4 E square sine to the 4th theta over 2, and then this 2W1 sine squared theta 2 over 2 W2. This is our result. In what you expect that W1 and W2, of course, are functions of the variables. The 2 variables P and Q, which we conveniently took to be Q square and U. Okay. And that will be a mess. You're never going to figure out what goes on. Okay, fortunately, around the same time when people decided to make experiments at SLAC, to look at this, Feynman initially started to look into the issue of the possibility that, and I reread the number of articles of Feynman. He says partons, and he puts in brackets quarks. Partons, quarks, okay, he was doing that. He had quarks in mind, and he took spin in 1/2. And so to see what goes on, you just pretend that there is this free parton. And why you think that it could be free? Well, this is the hope. There was an assumption, says this may be all wrong, Feynman is aware of that, but there is an assumption that the time is so fast, then the interactions by them may not be taking place. The energy is so huge, that means time is short. Okay, what does it mean the energy is huge? That is much bigger than the mass of the proton. Mass of the proton defines a scale which we call lambda QCD, remember? I'll remind you in a minute, once again. So it sort of made sense, even without having a full-fledged theory like QCD behind it that justifies all of that. So then we computed d sigma over d omega d prime for a parton equal quark that carries momentum, let's call it p slash, which is a fraction of massless quarks. Imagine the proton is made of the particles that basically carry no mass. That's again justified now today. The QCD picture justifies that. So that means that m quark square would be 0. Notice that m quark square would be psi square m square. And I'm not taking psi equal to 0. I say it all makes sense if m goes to 0. That's what I mean. If I have 1 over m, I have to keep it, okay, but I will always neglect m compared to q or the e prime minus c and so on. And we found out that we could cast in this form by having explicit form for W1 and W2, obviously. Then you compute them. And we found out from here, by computing this, the W1 in this picture, in the core picture, was, it had to do with a charge. There will be charge of the parton. Let me be very clear, quark square. Why not I just call them quarks from now on? Right? Because it's going to scatter a quark here. And then there was 2m. After all, what is the unit of W1? This has a correct unit for a cross-section. It's an area which is 1 over the energy square, and I'm dividing it by energy. So the unit of W is 1 over mass. And that's what we got. There was 1 over mass. And we also learned that X is that fraction of energy that the quark carries. And W2 was 2x squared m over q squared, which I can also write by using the definition of X as X m over nu delta. Sorry, there is a delta function. I don't know, what do I want to write it? This is equal to this delta c minus x. Obviously, there will be the same things we learn. We learned that basically immediately. It gave us an understanding what x is. Or if you wish, we now know what is that fraction that the quark carries. This is the scaling variable of Bjorken. This is called Bjorken scaling variables. I always keep wondering, okay, I've decided to write to some important people. They won't listen to me if I write to the Nobel Committee that there is this crazy thing that the father of all of this, and Zweig, who developed the picture of quarks, and Gell-Mann too, these people never got a Nobel Prize. This is amazing. He is the guy who told experimentalists what to do. Okay, I'll remind you in a second. They got the Nobel Prize, but not Bjorken. He's the recipient of our Dirac medal, okay, so. Many of our Dirac medalists, okay, some of the, this idea of Salan to introduce a new prize led to it become a major prize. Many people got the prize. So what do I learn here? Notice that this W2 is not a good variable because it's basically 0. Nu is huge. I won't see anything if I use this variable. Okay? I mean, this whole picture, you know what he does, is really beautiful, okay, based on the ideas of Feynman. That now you said, okay, the variable that you need to look at, he tells to the experimentalist, you have to multiply by nu and divide over m, because this is too small. So that becomes x delta x minus c. And when you change the units, you should also, the W1 then should be m times W1. And this is just 1/2. There is qp squared, q quark squared. The same factor is here. In both cases, delta x minus c. This particular thing is called Cullen-Gross relation. They actually obtained this relation of not all the details were fit in by Bjorken. The W2 is just 2x W1. You've seen the plot. I don't know if you had the time to look at the plot that I sent you. Did you have? No. The idea is to you to have a look, to appreciate that. No, if you look later, it's not the same thing you're looking at the moment when you are learning. Nobody printed it. Sure. Can you open the, do you mind having a look? Some of you have a computer here.
Mm-hmm. Scaling?
Right. It's more than clear, right? It's done, omega variable is 1 over x. Do you have at least some of you have a computer? Okay, why don't you can look at there, okay, you guys look here. It's really nice. Omega is 1 over x, they call it. But notice how clean this is, right?
Yes.
It's straight line, it's a
Yes,
function
yes.
of q squared. And q squared is right here in, can you see, I don't have my glasses, up to 8 GV.
GV.
Okay. It was not that large, right? We are not in the greatest of approximation yet. This is much more useful today, this picture, right? When q squared is really huge. Okay. Every day it gets more and more justified, the approximation we took. I'm deliberately slowing myself down, making sure that some question may emerge. As we are discussing this. I've also sent you, it was interesting, did you see this, the jet at least? Well, maybe you didn't see that. It's nice to see it all started with the thing of jets going back to back, you know, beautiful. This was at LEP, the opal detector. I think that was more than clear. Now, in order to really appreciate this, what it means really, the W2, after all this W2 that I wrote, which is here, let's look at W2 tilde, which has Q square, the charge of the quark I, then there was X. There should be also the probability. What really I mean by this, X now is, C is X, so I don't have to think about it. So the fraction that momentum carries is this variable X. And of course, this should be multiplied by the probability that such a quark carries a fraction out. Okay, this is called the Parton distribution function, which was figured out experimentally. Now, what would you expect? Did you look at the, I'm asking again what I shouldn't ask, right? If you didn't look at that plot, you didn't look at other plots. Well, that, okay. Not necessarily. Did you or did you not look at the PDFs? It's an interesting thing. Can you open it, please? Rico, I printed it. This is really instructive. So what you have inside the what do you have inside the proton? You have these quarks, but not just quarks, right? What happens is that, you know, if I have a quark, it radiates a gluon, and gluon produces a QQ pair, quark pair. If I have a quark, it radiates a gluon, which then produces whatever, gluons and so on. Okay, with the gluons is radiate off. So I have this. So what I expect is to have what we call valence quarks, which is the quarks the proton is made of, and the sea of quarks. What is the sea of quarks? Quarks, anti-quarks, gluons. Okay. So if you look at the PDFs, it's sort of interesting. Okay. You know, according to what we said, the Parton distribution function should not depend very much on Q square. On the left, you have very small Q square, and on the right, you have a Q square of today, of the order 100 GeV square. Notice that in the case of valence quarks, there is a pretty much stable thing that you would expect. There's the scaling. There is some small variation, okay? Not true when you look at the small x. Now notice with the small x, the C contributes a lot,
Yes.
You have gluons, but think of that. Small x means small energy. The fraction that this guy carries x times the energy of the momentum. The smaller the x, the more I'm in the strongly coupled regime, because when the energy gets smaller, the QCD coupling constant gets smaller. So these guys are not really free. So there my naive picture breaks down. I shouldn't expect that at small x, this contribution is tiny. Actually, it can be large. They can even dominate, and they do. The smaller the x gets, the more they can dominate, because we are not speaking of free quarks anymore. Okay? Here, intuition fails. Where intuition should hold is large x.
Yes.
The larger the x, the more the c should disappear. And that's what happens, okay? So this sort of is yet another confirmation of scaling. You know, there's a whole industry of understanding the evolution of these distribution functions through so-called Altarelli-Parisi equations. Okay, that's well understood. So this enables us today to match the theory and experiment. Next, for example, when I talk about the Higgs, I have to have I should be able to use the partons to compute the cross sections. Okay, I should improve that thing. Okay, but it all starts with this parton picture. And it all started with this innocently looking Lagrangian. It's worth writing once again. The QCD Lagrangian, which is just the usual kinetic energy. Well, let's write it G mu nu A. For our new photons, which are gluons, there are 8 of them. What is of course new, as you know, is that G mu nu A is d mu G nu A minus d nu G mu A plus F A B C G mu B G nu C, and there should be strong G strong. This is what makes all the difference in the world. This is what makes QCD behave so differently from QED, is their self-interaction. Okay. This is where Young Mills, you know, can serve even as a laboratory to understand gravitative self-interaction changes. The naive properties that you could have in your mind change dramatically when these self-couplings become more and more important. Then what else I have? I have a kinetic energy of, you give me a quark, I'll write a kinetic energy, and if you tell me that the quark has a mass, I will, maybe we should sum over all the quarks. It's a very simple, the fact that it's simple, of course, it's a bit misleading when we go to low energies. Okay, the dynamic is so complicated, and what we produce are bound states, which are pions and mesons and so on. It is simple only when I do the high energy. The crucial thing was the evolution of the coupling constant. I'm going to stop talking about this, so one last summary. The coefficient here was B3, we called it, of generic dependence. And we learned how to compute B3. That was 33 minus 2 number of flavors divided by 3. In the regime where you are above the flavor mass. That's all you have to remember. They run, these guys, they actually crawl at energies above their masses. And you see, this is coming from this. In QED, there will be just a negative coefficient, which has to do with the usual charge of the fermion. Okay. This is crucial. So it's all coming from this interaction. So for example, I'll have diagrams like this. When I'm looking at all the diagrams like this. Right, these are, no, why am I doing this again? There is a self-interaction when I square it, which is, sorry. Now, what I mean by this formula, that here, this is proportional to the trace of the generators in the adjoint representation, which we found out to be proportional to n, if you remember. That's how we derive the that coefficient. If you have a fermionic loop, on the other hand, that will be proportional to the trace of this, which is a half. So this is proportional to a half with some coefficient. So you notice when you do the running, for example, this dominates. I just want to tell you, when people noticed that you couldn't do perturbation theory at low energy, there was a deep puzzle what to do. So two pictures emerged. Eventually it was the lattice one, which was quoted about discretizing space. But the Troft had a very interesting idea, which is maybe worth mentioning, to work in the limit n going to infinity. N is 3, by the way. So you would say, well, that's crazy, right? Well, the idea was, he says, imagine that the coupling constant is a really effective coupling constant. Let me call this G0. The one I start with, let me call this G0. Divided by square root of n. Let me just introduce this sheet. Then these kind of diagrams would go, this is an example, would be proportional to G squared times G0 squared over n times n, which is, no, sorry, G0 squared times n, which is G squared. This instead would go as G0 squared, which is G squared over n. So in the limit n going to infinity, this you would neglect. That's what you mean. You would do the expansion in 1 over n. And if you're lucky, imagine that the expansion, you may laugh, but you know, we do expansion in QED, in E, and E is not small. What turns out to be important there is E squared over 4 pi, and that turns out to be small, so it all depends on the coefficient. There was some success, actually. A lot of meson physics was understood, some of the properties at least, by using this 1 over n, but it stopped short of proving confinement and so on. Okay, just throw this. Remember, we decided only one last thing I have to tell you, and it's in this collection, to define the scale lambda QCD, so that alpha 3 inverse of lambda QCD is 0, where you would expect this naive formalism to blow up. So if you plug it in here, this will be 0. You will get that 1 over alpha 3 at some energy E, often written, or the momentum mu, would be d3 over 2 pi logarithm E, or mu, over lambda QCD. You may see this formula, don't be surprised. This is just definition of lambda QCD. And it comes about a few hundred MeV. This is where strong interactions become strong, and therefore this approach of working with gluons and quarks you have to abandon. This is very interesting, by the way, because we have a kind of dimensional transmutation, whereas at large energies, you will talk about the coupling. When you come to the energies of lambda QCD, there is no sense to talk over strong coupling anymore. What is important is the scale that is responsible for the confinement, for the creation of bound states. And this would correspond to the masses of the particles, of these bags that you get, that we call proton or whatever. Okay. You're going to stop running the coupling and so on. You cannot do any calculation in the world, because any loop is as big as any other. You know, doing 127 loops is as big as doing one loop. So you can. This is where our we as physicists, you know, normally we just know how to do perturbation. Okay, I think I have nothing more to say here about QCD per se. and move to the Higgs. But now I know how to compute the cross-section for the Higgs production. I have to improve on the Barkham picture, but I can start from there and improve on that. These guys have strong interactions, I can include then the interactions. With the gluons, that's reasonably straightforward, you agree? Because the coupling is not big anymore. When I go to the energies of LHC, already at lab, okay, one number that I wanted you to remember. Okay. That alpha 3 at MZ, you will often cite it, is already small. It's 0.118. It's 1/10, right? LHC gets smaller, okay, I don't remember the number precisely. So we can do perturbation theory with any problem. And therefore you can then try to understand the plots that I sent you, which you didn't look at, okay? There is an art of understanding plot. We need to look at this plot. Let me, thanks. Let's open, there are two plots. Oh no, this is another one. Or maybe more than two, no, two plots. There is one which is just the branching ratios, but there is one which includes the production. The only thing in the one with the production, okay, that I took from Joadi's review, which is somewhat old, includes also the possibility of heavy Higgs. Today not so interesting. So let's look at the middle picture. Notice what dominates. Can you see what dominates? It's sort of interesting what you expected. Okay, no, the notation is the top one dominates, and that's what is called a gluon fusion. Two gluons. So let's start with that. So I have two gluons that produce the Higgs, and obviously they go through quarks. And which quarks contributes mostly? Because this is proportional to the Yukawa of the quark. So here we can say that the quark is top. The rest we can neglect. Other Yukawas are so small. By the way, Yukawas being small tells you why we couldn't see Higgs directly. There was no way of producing Higgs directly because quark masses are small, so if I do the EE bar scattering or PP bar scattering, PP scattering, I'll get nothing. I have to do it indirectly. So, and this is going to look like, this will have Higgs, and it has to be of what form? Is it going to look like, can it be like this? If it's Higgs is a color singlet, so I have to get a color singlet. Can it look like this? This is Lorentz invariant, right?
Different color.
I sum over colors. Repeating index is sum.
Okay.
No different color. It has to be color invariant. Higgs is color invariant. The interaction that I get, QCD is not a broken SU3 symmetry of QCD. Can this be there?
No,
Why?
because gluons are massless, and this is
Gauge symmetry.
gauge symmetry.
They're massless, so this will not appear. Okay, there is underlying local gauge symmetry, so I'm not going to produce this. So this is going to have the form G min wave, G min wave. And therefore this has dimension 5. So it has to be, let's call it 1 over, well, 1 over some m. Right. Now notice that when you do this, this could be a nice calculation to do for the take-home. This is a potential candidate that you guys can compute. These diagrams are finite, okay? When you sum the, well, the thing we will compute probably, I'll give you the decay of the Higgs into 2 gluons, or 2 photons. If I had 2 photons here, I would have F nu, right? That would be similar. I'm not interested into 2 photons producing the Higgs. I won't even talk about it because their coupling is small, okay? That's negligible. So if I am to do this integral just to show you, right, how would this integral look like? Let's call this momentum K. That would be d4K over 2 pi to the 4th. Right, and then we will have, let's take photons for simplicity. Let me not write the color index. Then I would have here, let's say, K slash plus m, K square minus m square, gamma mu here. I have to take the trace. There'll be gamma mu, there'll be, what is this momentum? Let's call this momentum P1 and P2. So this is K plus P1, right? K plus P1 slash plus m, K plus P1 squared minus m squared, gamma nu. I don't really care so much what is the denominator. And this is the momentum of the Higgs, let's call it pH. So this momentum is no, it's going this way, let's say. So this would be
K plus P1 minus pH.
So or well, I don't need that. Maybe it's better here.
Yes. Okay.
It's what? It's K minus P2. Maybe it's better. It's irrelevant anyway. Plus m, and then the dominant. So when you take the trace, notice there will be terms with 3 m's, and then there will be trace of gamma mu, gamma nu. Oh, let me just write down, there will be epsilon mu of P1 and epsilon mu of P2. So I just took photons, okay? Let's not worry about the coloring. So this will be proportional. The dominant piece, you could think, look at m cubed. What would m cubed give us? Well, there is this bunch of integral I have to do of the dominator. Trace of gamma mu, gamma nu. I will have gamma mu, gamma nu. That's g mu nu. So I will get m cubed times epsilon mu P1, epsilon, and whatever factor I get. This is nice to think about. This is actually 0. I cannot produce a gauge non-invariant piece. But you can try to figure out, okay, I'll leave it as an exercise, why this is 0. Okay, try to think about it, and then maybe you can come and ask me. It would be a disaster if it were not 0, because I would get a gauge non-invariant. So the next result, for example, 2 m's. Okay, I want to isolate dependent on m. 2 m's, what I have, 1, 2 m's, and then here momentum, but that is 0. The trace of odd number of is 0. So then I have 1m. So the actual result is proportional to 1m. So you get, what you get in this kind of thing, you will get Yukawa of that quark. You will get m4 coming out. But notice that the result goes as 1 over m. So what comes out, what will come out of this loop? I don't want to do the calculation, I'm lazy. it has to be 1 over m squared. Which m will come out? The largest m.
Mm-hmm.
I don't know a priori. If Higgs is very heavy, the largest m will be the Higgs mass. And so I will get for heavy Higgs 1 over mh squared, but Higgs is not very heavy. Today, you know, that was interesting to look in the past, but today we know what is very heavy. Top quark is very heavy. So what you are going to get here, and you can, this will be a nice homework exercise. Nice, well, you won't find it so nice. Maybe won't share my enthusiasm. You get a little of the computational tedium to worry about. That's illustrative. So this would cancel, sorry, let's write m cubed. So you will get Yukawa over, and there will be alpha strong coming up for the production, or alpha for the QED, if you look at the QED decay. And the subtles you get this, and then we said the only large Yukawa is Yukawa top, so what you get is G, Yukawa m top, there was 6 pi MW alpha strong Higgs. This is the coefficient that you get. I think so you see, alpha strong is not that small. I just want for you to get a feeling that this produces the important, actually, in this case, a dominant contribution at the let's look at the plot, if you wish. You have to go to very huge Higgs masses to start losing. Notice a dip, notice a bump in the cross section. Oops, sorry. Why is there this bump in the cross section? It's very strange. The cross section should fall down with increase of the Higgs mass. But there's a bump. Please look at the plot is extremely illustrative. I know it may be boring. Your capacity to do physics is the capacity to be able to understand those things without doing a detailed calculation. It will help you a lot. If you and I can figure out of understanding this, okay, we get an insight of how things work out. Why do you think that I have a increase of the cross section, which is nicely falling down? What could happen? Look at the diagram there.
The mass of mass of
Yes.
another quark.
This is the
mass of the
this is this diagram. It's coming from this diagram. The dominant contribution is the top. Well, if you have enough energy, you're going to produce 2 top from shell. That's better than being off shell. You're going to get an increase there. And of course, when the energy is much bigger, the fact that they're on shell is irrelevant. Okay? Remember that the cross section, you've studied this with Alexei. You always, in the single particle production, right? This is how you see the particle. This is Bright-Wigner in the single particle production. Here, the bump is maybe not so great. This is why we don't get a delta function. Otherwise, we would see the delta function and the cross section will blow up, but the particles decay, and therefore the delta function is just the Bright-Wigner. And the next one, can you tell me is what? Can you read?
Yes.
Yes.
HQQ.
HQQ. What is HQQ in your opinion? How will that go?
Boson.
Higgs to BB1? No, no.
No, if they say QQ, when you write Q, you don't mean heavy quarks, you mean light quarks. So it's not B. Well, let's do it here, and then we'll start drawing. Well, look at this. I have quark coming in. It emits a W or a Z. If it's a W, then up quark becomes a down quark or whatever. So I just call this Q because depending who I'm with. This guy does the same. Higgs. This is what's called a vector
Vector boson.
boson fusion. They fuse the two of them, W and Z fusion. This, as you can see, is very important. That's the next. Then below that,
WH.
WH. What is WH in your opinion? How will I get that? Oh, why do I erase this? No, this let me keep. So this is the gluon fusion. I'm not going to compute this. I'm just giving you a feeling how you could, okay? We want to get to, that's, you know, why this one dominates over the other one, that you have to put the numbers, okay? That I don't want us to see everything, to understand everything, okay? I just want you to know. So this is the WZ fusion. What else can I so this is called gluon fusion. Actually, I'm not a real phrenologist. I don't find that exciting. I can see that you are not very excited. But I still think it's important that you and I get an understanding roughly what is going on, okay? It will help you, you know, follow the developments, okay? So what could happen, you see, when I scatter, inside the proton there are quarks and anti-quarks. So I could have also anti-quark come in. Notice that we look at the distribution, there is an amount, there are less of them depending on X, but there are always anti-quarks. So I can produce here either a W or Z. So then there is a triple coupling. It's called the associated WZ production with the Higgs, associated vector boson with the Higgs. What else?
And you have ZH.
ZH. It turns out that WH is bigger than ZH. It's just the way the Z couplings enter, right?
Yes.
There was a peculiarity of the coupling that's not so obvious. And then?
TT bar.
And TT bar is separated, okay. Notice that TT bar, for example, can come from this. I could have also this becomes a TT bar, okay. That has to be much smaller, obviously. It's isolated. Why is it isolated? Because people want to use this to measure more precisely the Yukawa top coupling, okay? But it's very small, okay? This is obviously a secondary thing, okay? Now, what is very important, all that I want you to have, that this tells us how many families there are. This is not just producing the Higgs, this is a tremendous information. I know from here that there are no other families. How do I know that? Every new quark would contribute.
Yes.
So for example, if I have 3 families, then only top contributes. And it gives me, normalize it to 1. So add another family. You will have top contributing, but also T prime, BP prime. They're heavier, so they surely contribute. Their Yukawa couplings are big, so they contribute. So 1 will become 3, but you have to square it in the cross section, right? So this is 3 squared. So this is roughly 10 times the 3 family thing. Not to speak of having another family. Okay. This is beautiful. You and I can safely assume. There are 3 families. It's not so pleasant. It was nicer when there were 2 families. I tell you, life was better in the past. But it's one CP phase. We can live with that. Okay. The beauty of the standard model all of the CP violations to one phase. Okay, it's maintained. Okay, so this is the production.
One question.
Yes, please.
Sorry. I have heard also something called the strong CP phase. What is that? I don't know if you can talk maybe about that later.
That's it.
Yeah.
Well, if we should have at least one lecture on the sort of physics beyond the standard model, and that could be included. By the way, if you are, if you want to learn more, we can provide some lectures. The things that you always wanted to know and were afraid to ask. You can just come in if you wish. We can meet another 1 or 2 times, and if I know the answer, that sometimes works very well. I've done this in the past. The lectures which are not prepared may work even better because you have to think on your feet and discuss together. So that's very important, the strong CP phase. I don't talk about it because it turns out to be very small, but still important. The cross-section, notice the number, the total cross-section is roughly, it comes in the units of picobarn, these funny units, almost 100, right? Around 100 for the Higgs production. Almost 100 picobarn, and that is 100 times 10 to the minus 36 centimeters squared. This is a picobarn, it's very small. So that's about 10 to the minus 34 centimeters squared. The reason I want to mention the numbers a little bit, now you and I have to figure out how are we going to see, what are we going to see, what number, what is an idea of seeing number of events. So if I want to see something, I want to have as large cross-section as possible, obviously. But I also want to have my capacity that the two beings meet as good as possible. So that the collision rate has to be very good, if you wish. That's called luminosity. And it's a machine-dependent characteristic. As the time goes on, people learn more and more. You know, the technology, the development of technology, it's a fantastic thing. It's crucial. Okay, it's not just something trivial of having bigger and bigger accelerator. You have at the same time to have a more and more capacity. Cross-section becomes smaller, high energies of making sure that they collide. So the number of events, and let me write like this first, the number of events per unit of time is sigma times what is called luminosity. This is the definition of luminosity. Notice the luminosity has units in which is a number over centimeter square per second, normally given. This is the number of events per unit time. People often give you the number of events that sigma times integrated luminosity. This thing would be integrated luminosity. And the characteristics of machine left was around 10 to the 32 luminosity at left. So luminosity left was, L was around 10 to the 32 centimeter to the minus 2 second to minus 1. Just to give you. Tevatron, a PP bar machine at Fermilab. This is EE bar at CERN. Had a luminosity that started with 10 to the minus 29 up to 10 to the 32. These numbers, as boring as like me, are sort of interesting, okay? You'll see why. Because now there is a question of you're building a machine and you have a limited amount of time and money to build it. So it's a struggle to decide how big it should be and what luminosity you can. If you have more time, more money, you're going to do a better job. So it all depends on your expectations. If you want a better machine, it's going to take more time and more money to build it, but then there is more likely to find it, you know, and here it's a tremendous thing, okay? We'll see now. Okay, I'm going to ask you, I'm going to need your insight why we didn't see Higgs at left. And more interestingly, why didn't they see the Tevatron? Notice at the end, LHC, started at the 10 to the 33, and then went to the 10 to the 34 luminosity in the same units, okay? 2 orders of magnitude bigger. This tells you everything. It's not just bigger energy. You don't need much energy to see Higgs. The energy of LHC was decided to be so big that you could even see the Higgs if it weighted 1 PeV. But it doesn't weigh 1 PeV. You don't need all that energy, okay? Hopefully they'll discover tomorrow something new, okay? We're waiting, I can't wait anymore. I'm fed up. I want to do physics, the way I studied out, okay? In order to do physics, you need data, you need discoveries, okay? This was crucial. I will talk about that. And so then I want you to have this cell so that you and I can figure out the number of events. Just if you have, you look it up, or I send you a note with a summary of the numbers for some of you when you're bored and want to understand cosmology a little bit. So then the decay. How are we doing? We have still some more time. So let me leave the number for the production decay. What will be the dominant decay? You can look it up, but you don't have to look it up. BB bar.
BB bar.
Obvious.
Yeah.
So decays. We're going to talk about branching ratios. So you said the dominant one BB bar. Okay. And it's about 58%, it turned out. Next.
The second, like CC bar.
And the mass.
No, there is something heavier than C. Okay. Well, there is an off-shell W that is interesting. Okay, 2 Ws. If you look at the heavy Higgs, look at the heavy Higgs decays. You calculated that. That's the first one. No, I have a better plot. The second plot is better. Because this is the, notice that there is a plot which varies. This one is better. Because you can look at this vertical line on the other plot is the production. Okay, sorry. It's making noise. So,
And this.
right, it's interesting that the WW, of course, would be very important at the,
Heavy.
notice that it increases more and more.
Yeah.
You computed that. There was a longitudinal W, it went over MW squared. Yes. Remember for heavy Higgs, remember H going into VV was proportional to MHQ over MV squared. And that, of course, would dominate. Okay, that would have been beautiful for say people at Tevatron. They have enough energy. Okay, I'll comment on that. But the world is as it is. Okay, so WW is next, and it's about I think 22%. So let me write like this: WW star. Star I use for offset. Remember. Around 22%. Next. Now comes the the gluon is even bigger.
Yeah, the gluon.
The gluon is bigger, I forget that. It's about 9%, right?
Why?
Well, that's hard to see. I calculate the coefficient, but then you have to put we can put this rate. We can have that as a homework. That's not, once you have that, even if you don't know how to compute the decay, the amplitude, the second part would be fairly easy. Imagine I give you the amplitude, and you compute Higgs decaying into 2 photons. That you've learned how to do. You put the polarization. We've done things like that. Higgs decaying into 2 Ws. He is just the guy's master. So GG turns out, gluon, to be, what did you say, 9%? Or I said? I don't know. It's hard to see. Okay, I think I said. I heard myself say it. Then the next turns out to be tau. Tau is heavier than charm. Well, charm has color, but still this guy, and it's about, I think, 6%. Then comes CC bar, I think about 3%, about half of that. That's what I roughly remember. Let's see, where am I? 80, 89, 95, 98. There is also ZZ. Look how the numbers conspire. This is a pity. Another bad luck for Tevatron. This is only 2%, but this is clean. Much cleaner than this when you go into neutrinos or hadrons, which is harder to see quarks. This goes into lepton pairs. This is very clean.
Yes.
But it's only 2%. Now, if it were the other way around, you had an order of magnitude improvement. And notice the luminosity at the at the end, the Tevatron has luminosity which is order of magnitude smaller than CERN at the beginning. So imagine that they have 30 events. They will have 3 events. With 3 events, you can claim something. You can't prove a discovery. But then everybody has to sort of acknowledge it afterwards. People, they do that. Okay, the original discovery of W, there were 3 events. I think they were not even true. The first 3. It's another one. Okay, there were a lot of afterwards. And this adds up to more or less 100%. Why? Because the other branching ratios are terribly small. There is, let's write them here, there is gamma gamma, which is about 2 in 1,000. There is also SS bar, which is similar. There is mu mu bar. Oh, this is important to comment, which is about 10 to the minus 4. So this is 10 to the minus 3, let's say. I don't know why I need this factor. And it's practically 0. Okay, so this 0 was how Higgs was found. There were 2 things, okay? This 2% was also useful. Both were very important, okay? More or less going at the same time. As the time went on, okay, this became more and more important. So let's try to put the numbers. For example, gamma gamma. Let's see gamma gamma. I think we understand that. I don't know if you have to say anything about the case. You want to ask me something about the case? I don't think I have anything. Oh, there are questions we should ask. Okay, let me ask you questions just to see if you are quick on your feet. Oops, why did I lose it? Move on the other page. No. Tell me one thing. Look at the ZZ. It grows until a certain number, then it falls down. Why does it fall down?
It goes to another particle.
Please. it's ZZ there.
It's a pair production tau.
But everything goes down there.
Yes.
Why? And then it will grow again.
Because
ZZ will grow again. It has to grow. ZZ. That's why I ask you about
the
Z.
W mass.
It's 2 times the W mass, precisely.
Yes.
You see how interesting you can get information. Now you produce these guys on shells, so this guy gets boosted tremendously. Okay. After all, of course, it won't matter. Again, this is very important when you are sitting there, right? It's this resonant thing. Okay. Is there anything else that we could ask ourselves? I think we understand why gamma gamma and Z gamma are small. They also grow and fall down when they're around there. Mu mu we expect to be small. I don't think I have questions here. So what we said, remember, and you guys knew that, you had enough intuition that BB bar is always 58%, was not the best channel to look at. This is being now.
He explains invisible. Or something.
You put some limits on Higgs going to invisible. I can't quote them very well. I can try to answer that. I don't remember the number, of course. There is still possibility for some invisible channel, for sure. Do you have an idea, okay, how, at least an order of magnitude for the decay bits of the Higgs? W and Z, you remember? I want you to have feelings, and you should remember. What is the mass of W and Z? 100 GeV. I'm asking you roughly, 100 GeV is good enough for me. So what's the decay bits? It's a coupling times the mass. What else can it be? It has a dimension of mass, and it's going to be the coupling of the mass, and coupling is roughly alpha or pi over 10 to the minus 2. So the decay bits of W and Z must be over the GeV.
Yes.
I'm asking you an order of GeV. I don't have to do a calculation, okay? The Higgs, you expect it to be smaller, bigger? The mass is more or less the same. For you and me, it's the same. It's 100 GeV. So let's take, they are all three having mass of 100 GeV. We are very rough. Do I expect more or less?
It should be the same. But the coupling.
Coupling is smaller.
Coupling is smaller.
Well, the most it does, look, the feeling is here. 50% to 100% for me is the same, I'm estimating, okay? So this is 100%, okay, factor of 2. But coupling of V, you cover B. Whereas in the case of W, the coupling is G. This is MV over MW. So it's highly suppressed. That's why the decay bits of the Higgs is actually an NeV. If you know the AV, you get a lose a factor about 10 to the minus 3. Okay, just remember that. Okay. It's a very narrow resonance. That's nice. It's nice to have a narrow resonance in well-defined particles. Okay. So now let's try to talk a bit about the irony of life. I mean, the Higgs, the whole story of Higgs is sort of amusing. There is a story that Higgs was giving a seminar. I don't know if it was at Harvard, and lectures simply never, they missed each other, they were going to take coffee, they were supposed to discuss this. Suppose you're working on the standard model and you know that there is a Higgs mechanism you would apply it, okay. That was missed, okay, it will be done later by Weinberg and Salam. It's interesting now, the discovery, okay. So, left. Let's go to left. Where for left, I need a production, I don't have a production cross-section for left. The one that I said was not so important. If you look back at the production, why did I close that? Look at the production at the LEP-like collider at 500 GeV, the last plot. The three of them. Okay. Look at the channel. There are two channels. The only two channels that matter, right?
Yes.
Are H nu bar,
and
HC. Well, the H nu bar is the analog when E and E bar come into it. This is a W fusion, you agree?
Yes.
I noticed that at 500 GeV, this guy is even more important than the associated production. The lower, however, the lower the energy, the harder it is to produce the nu bar. You see, imagine that the energy is very small here. Then this W is more and more of shell. When it's of shell, the cross-section is suppressed. So at LEP, this is basically irrelevant. At LEP, the thing that mattered at LEP was this. You see all of you this, right? Was this associated production. But the associated production, in order to see the Higgs, you need energy which is bigger than, in order to see the Higgs, you need energy of bigger than 125 from 19, this would be 215 GeV. This is what you need. The energy that they had of LEP was around 200, 205, I think. Bloody hell. For 10 GeV or 15 GeV, you must eat your hearts out. You spend your life looking for a bloody thing, okay? They had everything. It would have been a clean event. You know, you see the C boson, you see the Higgs nicely indicates. It's an electron machine. It's not full of these debris of quarks and gluons that obscures everything, you know. It's like looking at a microscope. There are two bad lucks. This thing killing you by the cross-section being small. They had enough energy to see that because this is Higgs with neutrinos. They had more than enough energy. But the cross-section is small. It's going to be, it will be great if that's what they're going to build 500 GeV. This will be a beautiful thing to look at, okay?
Yes.
You're going to see the Higgs and then you will check all the couplings. If you look at the production in the new lab, let's call it E-lab, extremely large electron, I don't know, I should think of a name. Maybe send suggestion, maybe they need a name, you know, good name. Catchy name, not just linear collider or big linear or whatever they want to. Then they still want to look at HTT bar and so on, okay, because you want to measure these things, okay, but they are small. So this is lab. There were people who said that the guys at LHC should get the Nobel Prize. I don't know if you've heard that. The craziest thing I ever heard. These guys did the same thing that everybody else was doing. All they have to do, all the physics was understood, all the cross-sections were computed, okay. They just had a better luminosity and more... it's a great work what they've done. I don't want to doubt it. But to say that that merits a Nobel Prize, I think, is offensive. As you can see, I have strong feelings and I strongly express them. Tevatron. And LHC. So we decided to look at two modes and I erased them. Can you remember them? Gamma gamma? About 2 to the minus 3. It's good that I erased. And WW star? ZZ star.
2%.
So this is 10 to the minus 3, this is 10 to the minus 2. Okay. And what was the sigma total? Try to remember that number. 100 picobars, more or less. Well, it's a little less. I'm going to be rough here, okay? So sigma here, to produce H gamma gamma, H going to, sorry, sigma pp, let me write, sorry, H to gamma gamma, 10 to the minus 37 centimeters squared. Sigma pp.
Is it 10 to minus 2?
Sorry?
The ZZ star.
ZZ is 10 to the minus 2. I think that's what I said. 2%.
2%. Okay.
Yeah, 10 to the minus 2.
Yes.
H going to ZZ star is 10 to the minus 36 centimeters squared. Luminosity. I remember that sort of the year 2012, the summer of 2012 is interesting. By the summer of 2012, Tevatron has integrated luminosity of about 10 inverse picobars, so that's 10 times 10 to the 36 centimeter to the minus 2. That's 10 to the minus 35 centimeter to the minus 2. No, 30. No, plus, what am I talking about? 10 to the 37, right? It's interesting. They have order 1 event, but of the 10 events. They actually looked more into around 160 GeV. It was harder to look into smaller. It was a question of background and so on, it is true. I still don't know to these days. I would love to figure out, to talk to someone. Was it just bad luck or they didn't believe enough? They started to see it, by the way. They were announcing it. It's just that those guys discovered they had more events.
I'd like to see.
They were so close that they were already about to indicate the possible signal, though other guys could claim discovery. You see, if you have an order of magnitude bigger event, then 10 becomes 100, and then you can eliminate the background, you can clean it, and eventually proclaim, right, this is our famous 5 sigma. We can talk about the probability has to be 99,999,999, 6 decimal places. Because there are so many fluctuations that you find in these experiments that the final agreement is to have a huge probability, basically 1. But they were there. Just about to do it, okay. Well, with an order of magnitude extra luminosity, the rest is history, we can say, or so it seems. Higgs was discovered. So what has been measured is, this is done very well. Finally, tau bar last year indicates the same 125 Higgs in a good agreement. BB bar is being doing now, 2017, as we speak. It will be only a question of time to come to 5 sigma, okay, it's now a question of time, then you give them time, integrated luminosity grows, okay. So BB bar, the interesting thing is that is mu bar. It's true that there is an order of magnitude less, but we are going to know this with time. I wonder whether they're going to say that it's 1 year, 2 years, okay, I'm not an expert of this, I can't speak with authority, but it's only a question of time. So you and I could hope maybe that they see some deviation. Depends how you feel about it. Deviation means that there is something more to it. I want to see it confirmed. I believe in the standard model Higgs. Everything that I've done was a belief that the standard model is a good theory at low energies, or most of the things I've done. And then there may be deviations at high energies, okay, but to be honest, any deviation from standard model would be more than exciting, okay. We are desperate for indications of new physics, okay. So if people ask you when you hear this that we found the Higgs, we must be very careful. We found a particle that starts to look more and more like the standard model Higgs, but we are very far from, okay, the top quark coupling is measured, okay, this is good, but we need more. We need CC bar. One day we would like to see the electron. That will be the crucial thing, that even this light path, no hope at LFC, right? This is an order of magnitude, orders of magnitude below. So the moral is big, build as big luminosity. That has been a tremendous lesson. People took it out seriously. All the people talk about more and more is luminosity. Okay, the size of the machine, you know, that's often limited by the space where you can build it, and that's going to be limited by the, of course, amount of money gets harder and harder. Okay. I think I can stop here. Questions, please.
One question. Do you think that it is a good idea to build another accelerator?
Of course.
Like
I have no doubt.
In China, that is going to be like 100-kilometer circumference.
100, right, whatever you could do. I mean, biggest.
100.
There were always a discussion that we will go in, throughout recent history, especially. In the old days, there was no doubt. For us, accelerators was a hammer is for a shoemaker. Okay, shoemaker is not going to make shoes without hammer. You and I cannot talk about particle physics without seeing really what happens. This claim that I can do a low energy experiment, as beautiful as it is, it's a nonsense, because I have to see inside the phenomena that I talk about. The question is, of course, only a question. Now you may see, well, there is a problem of money. It was very interesting when in the 80s, Glashow was in particular insisting in a beautiful manner about building at the time they were going to build a super collider in the States. So there were three schools. People that didn't want to build it. Usually they were non-particle physicists.
Yeah.
Well, the more money goes into particles, you can understand them, okay?
Yeah.
I don't have anything to say to them. Then there was a second argument, you should build this machine because you're going to discover some kind of final theory, you know, the origin of the universe. That's a lousy argument. Glesher was saying, all you have to convince the people that give you money that we need this is our tool. The second, that we delivered in the past. Every time there was a surprising discovery. And not only that, there were great advancements, like internet, that was needed, right? The web was a product, basically, of LHC, or bilingual, in order to process all that information, okay? Finally, an incredible technological, social, political advance. And the thing is that what I remember this sort of in the 90s, he pointed out that what you have to change now is not many little labs that you had before. They have to become more and more international. And that's, in some sense, it's also beautiful, right? Us, like the same thing that we have us here for more, you know, parts of the world being together would make it even more necessary for the advancement. So he was making a claim, and I think there are people who justify that actually you don't have to spend more money. You just have to come together. Well, coming together is not easy. We need people to agree to come together. So now Europe that managed to come together, Europe went through the past of a great enthusiasm of unification, right? We know that there was money. Europe is, you guys read, maybe not being Europeans, you don't care as much. You see less enthusiasm these days and more worry about stabilities and the economy. Now Europe is absolutely unwilling to find money for. The only thing we can hope maybe would be upgrade of LHC. Okay, to build a very high luminosity machine. That'd be great. It keep improving luminosity. Remember, it's not just energy, it's luminosity too. Okay. But anyway, I'm making it long, a short story. Yes, we definitely need. And not we, you more than me. Okay, it's all that. Now, you may want to not do particle physics, but cosmology, I want to tell you there may be great excitement. This is still the time. I still may convert one or two of you, you know, I'm on a mission, as you can see, okay? Making sure that you don't listen to false preachers, false prophets, sorry. Any more questions before we close the shop?
We can close.
We can close it, okay?